Hey guys, Mr. Deedless here. Let's talk about some forces. So, we're going to talk about the stuff that my buddy Mr. Isaac Newton had developed. He invented physics, he invented calculus, and he invented a few other things as well. So let's go ahead and get started. So, firstly, inertia. Inertia is the tendency of an object to resist a change in motion. It is a qualitative description of essentially mass. Mass is the measure of inertia of an object. It's a quantitative number, it's a description. And the SI units for mass is kilograms. There are no units for inertia, well, kind of, because inertia is more of a descriptive thing. If there was units for inertia, it would be kilograms, because inertia is pretty much the same thing as mass. It's just that when you say something has a lot of inertia, you're just kind of describing how it's going to behave. If you say it has a lot of mass, okay, well, exactly how much mass does it have? You can give a numerical value to it. Otherwise, inertia and mass are virtually the same. Mass and weight are not the same, and those are often confused, so be very clear about that. So where mass is an inherent property of an object, it's how much mass it has, how much stuff there is, it's measured in kilograms. The amount of mass it has will never change regardless of where it is. Weight, on the other hand, can change depending on location because it is dependent on gravity. So if I go somewhere where the gravity is weaker, then your weight would be less. Weight is quite literally the force of gravity. They are synonymous. So if I go to the moon where there's 1/6 the gravity, I'm going to have 1/6 the weight, but still the same mass. So be quite clear on that. Newton's first law of motion. So he has 3 laws of motion. He has other laws as well, but there's 3 laws of motion. The first law is, and I want you to know these words precisely, just like this. An object in motion stays in motion, an object at rest stays at rest, unless acted upon by an unbalanced, non-zero net force. And this is also known as the law of inertia. So what does this mean? Well, it basically means that if I have any sort of arbitrary object, and there we go, and so there's my arbitrary object, that object is going to stay stationary unless there's some sort of force input onto that object. So is there a force? Okay, well, let's just say that there is a force of gravity acting down. I'm going to denote that with an F and a subscript G. G, there we go. Sometimes that can be described with a capital W for weight because they are one and the same. But regardless, there's a force acting on it, so therefore it will move. There's an unbalanced force. Unless that thing is on a tabletop and there's an equal and opposite force acting on it, keeping it from accelerating, and so there are balanced forces, therefore it will remain at rest. If there is not balanced forces, then it will not remain at rest, and it will continue to move whatever it's doing unless there is an unbalanced force. So what if you have an object that is in deep space, nothing else around, and it is moving in this direction with a constant velocity? And just put a little bar over it to mean that that velocity is in fact an average constant velocity. It will continue to move in that direction forever unless there's some sort of unbalanced force to pull it off of that motion. So object at rest stays at rest, object in motion stays in motion unless acted upon by an unbalanced non-zero net force. Newton's second law can be stated in essentially these terms, which is my preference. There's lots of words you can use, and that's the way he had initially put it, but we're basically going to say that the sum, this is the summation, the sum of all forces equals mass times acceleration, which is equal to force 1 acting on the object plus or minus force 2 acting on the object plus or minus force 3, and so on. So essentially that means that any object is going to accelerate, okay, it's going to accelerate due to a force. So if this is the only force acting on it, then it will accelerate equal to this rate, where we take the mass of the object, it's going to accelerate at this rate. So if I were to take each side and divide it by m, I would get F over m equals a. And so if I take that force, divide it by the mass, I'm going to get an acceleration. What you should recognize here is a couple things. For one, that the force and mass are proportional, force and acceleration are proportional, meaning that if I were to increase the value of the force, I would also be equally increasing the value of the acceleration. So if I double force, I double acceleration, given that there's no other forces acting on it, and that is something very clear. Mass and acceleration are inversely proportional. Let me rewrite it here. So F equals ma. So if I were to decrease the mass, given that force stays the same, and whenever I want to compare two things, I'm always assuming that anything else that I'm not describing is going to stay the same. So if mass decreases, how does that affect acceleration? Well, given that force stays the same, because I'm not talking about force right now, given that mass decreases, what will happen to acceleration? Well, in order to keep this the same, acceleration must increase. So if mass is halved, then acceleration will be doubled. That is inversely proportional. Okay, so let's take a look to see what happens if there's any other forces involved. So let's see if I can draw in another force. So let's say that there's some sort of other force acting in this direction, and it's a smaller force. So vector addition would show these two forces. So let me draw this one. So I'm just duplicating that force. And then I also have tip to tail vector addition. I have this other force as well. So I'm trying to keep them fairly the same size as what I had. And then the vector addition of the two should go from the very beginning, right? It starts from where this one had started from the very beginning, and it's going to end in line with this one. Okay? And so that's my resultant. That's my resultant force. That is otherwise known as the sum of all forces. The resultant force and the sum of all forces are the same thing. So my net force, okay, there's resultant force, sum of all forces, net force, those are all the same thing. Net just means after everything is summed up, what do you have in the end? So your net pay at the end of your paycheck is what you actually get into your bank account. Gross pay versus net pay. Okay, so let's look at this scenario again, where if I were to double the force and I get double the acceleration. Let me look at this example here. If I double the net force, I get double the acceleration. But is that true if I double my applied force? Well, let's take a look. So I'm going to apply a force. That's the black arrow here. So I have an object and I'm going to apply a force. That's the black arrow. If I were to double that, would I also get double the acceleration? Okay, let's take a look. And by the way, whenever you're getting some sort of conceptual question, always think of the extremes. So the extreme I want to express here is this. What if I have a force? Let me make this one more time. I'm going to redraw all this. In fact, let me back up a little bit. And tell you what, I'm going to even delete. Okay. So let me express it like this. Okay. So I have double the force, double the acceleration. Now this is net force. What if I just simply double my applied force? So here's my example. I have a very large force and I have a very large, actually, no, maybe I shouldn't make my force quite so large. There we go. And so that is my applied force, and then I'm going to make a friction force, let's say, that is something like this. So it's got a very small net force. My net force is very small. Okay? So this would be like a scenario. We have a tabletop and a box that is on that tabletop, and I'm going to apply a force in this direction, and then there is going to be friction in the opposite direction. This box is going to just barely accelerate. It is accelerating, but just barely. It is picking up speed, it's moving faster and faster, but just barely. You're only just barely overcoming friction. What you should recognize is that this much of your force, that much of your force right there, is just overcoming friction. The whole point of that amount of your force is just there to overcome friction. You must also understand that as you increase speed, typically things like friction do not also increase. So we'll get more into that in a moment. So what happens if you double the input force? Okay, I'm going to draw another arrow here to represent that. I have added in another input force. So it is double the force. Now your buddy is helping you to push this box. The resistance force, the friction force, has not changed. So I'm just doing tip to tail vector addition. I can order these around however I want. Tip to tail, and then my resultant force is no longer this little tiny thing. Now my resultant force is now this very large value. Look at what happened. So in this case, I might have doubled my my input force, but my resultant force has well more than doubled. So you must consider that when there's more forces involved, just because you double one force does not mean that the resultant force increases, and that does not mean that your acceleration necessarily doubles either. So in this case, your acceleration would not double. It would, probably times 10. It would increase dramatically. Okay, that is something serious to consider. All right, so that's my basics on Newton's second law, and this would be the F1 plus F2 plus or minus F3. So F1, F2 minus F3. Let's look at Newton's third law. So his third law of motion says that for every action force, and I really want to bring focus on the word force here. Actually, I had capitalized the word action. I think actually I meant to capitalize the word force. So for every action force, there are an equal and opposite reaction force. And I'm focusing on this because it's usually not added, but I found that it eliminates a lot of confusion to add in the word force. And here's why. It is the force that is equal and opposite, not the acceleration, and that is often the point of confusion. So for every action force, there is an equal and opposite reaction force. Keep in mind that forces are always in pairs, known as action-reaction pairs, and that these pairs always act on opposite or different objects. So if I push you, you push me, right? We are different objects. Well, here's an example. What if I have a ball on a string, and you're holding up the ball on a string? So, in fact, I suppose this seems reasonable. So it's the time of your hand sanitizer, and I'm sort of have like a string. And so as I hold this on some sort of string, the question is if I determine that and there's lots of forces happening here, but if I were to focus on one set of forces, the force of gravity here, if I say that the action force is the force of gravity acting down, and so if I were to draw that here, I would say that, and I'm going to always go from the center of mass. So the force of gravity is acting down, okay, from the center of mass. The force of gravity is acting down on the ball or the hand sanitizer. So center of mass of the hand sanitizer, the force of gravity is acting down, and we always want to treat the string to be massless whenever possible. So if that's the action force, the question is, what is the reaction force? Think to yourself. Come on, it's wait time. A lot of people will say it is my hand pulling up on the string, or the string pulling up on the hand sanitizer, but it's not. Those are forces still acting pretty much on the hand sanitizer. I push you, you push me. Just reverse the wording. If the earth pulls down on the hand sanitizer, then the hand sanitizer pulls up on the earth. And it does. The hand sanitizer is in fact pulling up on the earth. It does have mass. It does in fact have its own gravitational field. Whether you want to consider it or not, it is there. Is it negligible? Yes, because I cannot measure the amount that the earth is really accelerating up. And here's a crazy idea. When I drop the hand sanitizer, The Earth causes this to accelerate down. This causes the Earth to accelerate up. An amount that cannot be measured, but that doesn't mean it's not there. Okay? So, the forces are equal and opposite. In fact, I can kind of put all the laws together in this way. The force acting on the sanitizer by the Earth is equal to the force, actually I should probably put a negative there, is equal to the force acting on the Earth by the sanitizer. Those are equal and opposite, and I often just to kind of prefer to get rid of the second subscript there. And so essentially the two forces are equal, and in fact what I'm going to really express is this, is that, let me just say that the force of the sanitizer is equal to the force of gravity on the Earth. And so the mass of the sanitizer times the acceleration of the sanitizer is equal to the mass of the Earth times the acceleration of the Earth, right? So if this is a very small amount, then it's going to be a very large amount. If this is a very large amount, then it's going to be a very small amount. So this is why with the mass of the Earth being very large, you don't notice its acceleration because it's so absurdly small. However many times greater the mass is, the Earth's mass is than the mass of the sanitizer, I know that the acceleration of the sanitizer is 9.8 meters per second squared. Well, however many times greater the mass, the mass of the Earth, long day, the mass of the Earth is, however many times greater that is, that's how many times smaller the Earth's acceleration is. That's why it's so absurdly small and negligible. So let's move on. Those are Newton's 3 laws. See if you can apply all 3 of them to a scenario. I always like the scenario of a bug hitting a windshield. Here's an ugly, ugly car, and then so here's the bug. Right, there's its wings, minding its own business, and then a car comes in and zoom, hits the bug, splat goes the bug. And so, what's the last thing that went through the bug's mind? Its butt. But beyond that, how do we apply all 3 of Newton's laws? Well, let's start with the third one. Which force is larger? The force of the car onto the bug or the bug onto the car? Now remember, the bug gets smashed. So the car must have a larger force, right? No. They're the same force. They're the same force. What's different is the accelerations, right? Just like I had expressed here, okay? The bug has a small mass, so it has a large acceleration, given that it's the same force. Bug small mass, large acceleration. Car, large mass, small acceleration. And then let's go back to the first law. You don't have to do these in order. Go back to the first law. The car was in motion. It has a lot of inertia. That's why it's the law of inertia. The car has a lot of inertia. It was in motion. It wants to stay in motion. And there really wasn't a very significant force to an unbalanced force to bring it off of that motion. So it just kind of continued minding his own business, like the bug just should have been. So let's talk about inertial reference frames very briefly. Inertial reference frames are they're reference frames in which Newton's first law is valid. This usually excludes excluding and accelerating reference frames. So for example, if you were to have a party in the back of a giant moving truck, okay, you're just having a good old time, and all of a sudden everybody in the party in the back of the moving truck slams up against one side of the truck, you're gonna be like, what just happened? I mean, what if you didn't even know you were in the back of a moving truck? I know this seems weird. You were kidnapped, and you're like, all of a sudden there's a party going on, like, woohoo, physics party, let's do experiments. And then, so you're just kind of like, mind your own business, it looks like a normal room, just with no windows, and all of a sudden you slam up against a wall, and somebody goes, oh, don't worry, you were just in the back of an 18-wheeler truck, moving truck. And you go, well, that's weird. Okay, well, what happened? Did the truck driver slam on the brakes? And you don't know. right? Because assuming that you're going down the freeway at 100 miles per hour, super smooth road, you didn't even know you were going it. You don't know if he hit the brakes, if he hit the gas, or if he was turning. And so if he's constantly turning, you must now recognize you are in a non-inertial reference frame, because it seems as if there's some sort of like force pushing you up against the wall. And so you must have to take into account for that. And so Newton's laws shouldn't account for the fact that it seems as if there's a force pulling me in that way, even though there's not in that scenario. It is just simply your inertia keeping you moving. If you were moving something in a moving truck and you slam on the brakes and something heavy that is not secured, it is going to slam into the front of the truck. I've had it happen. And so that is inertia. Object in motion, if it has a lot of inertia, it's going to want to stay in motion until, well, when I was a kid, my mom used to keep all of her junk behind the rear passenger seat. She'd slam on the brakes, hit me in the back of the head. She just loved to torture me. It was great. How does a rocket move in space if it has nothing to push against? Well, it's easy. They bring all the stuff to push with them. Think about this. In order to go to space, you have to bring all the stuff to push with you. So the International Space Station right now has to make minor adjustments in its orbit. And it must have gas, some sort of fuel to push, and it expels that fuel at high rates of speed, so that way the fuel goes one way and the International Space Station goes the other way. That's what rockets do. They expel gases out the back, downward at a very high rate of speed, so that way the gases then in turn push the rocket upwards. This is fun. Next time you walk across the room, think about this. Instead of thinking, I'm just gonna walk that way. Instead, think, I'm gonna push the floor that way. Do it, for real. Do it. With every step you take when you walk out of your room right now, think with each step like, I'm gonna push the floor that way. Try and actually push the floor behind you with each step, because that's what you're really doing. You're trying to push the floor that way, and the floor is in turn pushing you that way. That's what you're doing when you walk. So I did say that weight is the force of gravity, so we're going to express that with an F sub g. Sometimes it can be a capital W, but I much prefer it this way. And instead of saying ma, we're going to say mg, where g is the acceleration of gravity. It is 9.8 meters per second squared, or about 10. And we can usually round it off to 10 meters per second squared, and that's just fine. When we draw a free body diagram, we're going to express it by drawing an arrow from the center of mass acting down, and I'll get more into that. The normal force is a force that is perpendicular to the surface, and so we're going to draw an arrow that goes from the contact point between the box and the surface. And since this box is not accelerating up or down, or at least I'm going to assume that the table that it's sitting on is not accelerating, so therefore the box must not be. And so these two forces must be equal and opposite, but not because they're action-reaction pairs, right? The reaction force for each of these would be drawn on a different object, right? The force of gravity does have a reaction pair, but that force is going to be on the Earth. So if this was the Earth, then from the center of the Earth, I'd be drawing a force, and this is clearly not proportional, nor is that really an arrow. Whoops. There, something like that. And so since the Earth is absurdly large, it is not rational for me to try and draw that at all, is it? By the way, whenever we draw free body diagrams, we want to draw a different diagram for each individual object that is in the system. And so I'm not going to bother drawing the Earth. I'm only concerned about this one object. So here's free body diagrams. If I have this scenario, how would we draw the free body diagram acting on it? As I just said, we would draw a different diagram for each individual object in the system. So we have two boxes on some sort of table. There is friction between the boxes and the table. there's a string attached to each box. So you're going to pull with your hand, that's my beautiful hand drawing. You're going to pull to the right onto this box, and then this box is attached to the other box with a string, and so clearly that one's being pulled as well. I've already gone ahead and started by drawing the gravity and normal force, and so the normal force being that force perpendicular to the surface. And so here are those forces acting on it. Again, those two are equal and opposite because it's not accelerating up or down. But what else do we have? Here, let me go ahead and switch to my my arrow. And so if I have a force acting to the right by the person acting on this box, so let me just kind of draw that one. Okay, so I'm just going to try and make it about the same length as that. And so I can label that as the force of the person. Let's see if it'll let me do that real quick. All right, so that is the force of the person. And then acting in the opposite direction, I have a, well, what force do I have acting? Actually, you know what? Let's forget friction for a moment. I can still add that in, but give me a minute. What if instead I just focus on the force of tension in the string? Okay, so I'm going to draw the force of tension. And I'm going to assume that these boxes are in fact accelerating. So I'm going to make sure to draw this force smaller than that force, which means that there will be a net force acting to the right and the box will be accelerating. Well, that same force of tension is acting on this box, right, causing it to be pulled. Force of tension, there we go. And so these are actually an action-reaction pair. If I get rid of one, I get rid of the other, right? These are actually an action-reaction pair, and they're drawn on different objects. And so, yeah, that's it. That's all I would be drawing if there was no friction involved. I would be done with my free body diagrams. Let me go ahead and see if I can draw in friction as well. Or not, because my video just quit. That's no fun. See if it'll come back up here in a minute. But in either case, you've got this guy, so I've got friction. Okay, let me do friction. So let me add in friction. And I don't want to make it too big, that's the force of friction. And then I'm going to also add in a force of friction here. But these force of frictions are not necessarily the same. They're different because they're different objects. This one weighs more, so it's going to have more friction. What I should note is that this force of friction should not be, like this force of friction and the force of tension should not be larger than the force of the person. Like these two added together should not be larger than that. It can't be, because otherwise it would be moving like backwards away from the direction you're pulling. And frankly, that would be weird. Still no video, but I'll have to just move on. All right, I've removed that camera and switched to a different one. Grainy, but oh well. So let's kind of get this thing done, almost done. So keep in mind that you cannot have a force of friction that is larger. All right, so let's move on to what is friction. So we have two different types of friction. There's kinetic friction and static friction. Kinetic friction is equal to the coefficient of kinetic friction times the normal force. And so what does that mean? Well, let's kind of look at this. So what is the friction force equal to? It is equal to the coefficient times the normal force. Okay, so normal force, let's think about that. So there's a force of gravity acting down on this object, and there's also a normal force. Now, if the box weighs more, right, if it weighs the force of gravity, if it weighs more, then that means the normal force must also be more. If this is more, then this must be more. What is the coefficient? The coefficient is basically just a value of the two surfaces rubbing against each other. It is a property of the material itself. So if you were to zoom in on the transition point between these two surfaces, you would see that they are rigid. And so it is essentially, the coefficient is basically a function of just how rigid and sticky those objects are. And there's a different coefficient for different materials. So So for example, if you have rubber on concrete, there's going to be one coefficient versus rubber on rubber. Rubber on concrete is usually a coefficient of about 1. If you have a coefficient smaller than 1, basically means that it's a little bit more slippery. If you have a coefficient that's close to 1 or even more than 1, it's extremely sticky if it's close to 1 or larger than 1. Now, I have here that the force of the person is acting up and away from the table. That's actually more efficient than just trying to pull directly horizontally. Why? Because part of your force, wait, let me draw the components of this force. Let me back up just a tiny bit. So, in fact, I'll switch color. So if this person, okay, I'm going to break this down into its components. Only this part, right, the force of the person in the x direction, only that part of their force is actually acting into making it slide along the table. So that seems wasteful, right? This part of the force is not going into moving the table, the box along the table whatsoever. That is the force of the person in the y direction. So why is it more efficient to do this? Well, strangely, in this case, the force of the person, this is unweighting the table. It is reducing the friction force. So there's a certain angle at which you are most efficient dragging a box along the floor by pulling up just a little bit at least in order to unweight it, and then it makes it easier to slide. What is static friction? Static friction is the friction between surfaces that are not sliding, not moving, sliding, and that's the key. So once an object starts to slide, okay, so if the two objects relative to each other are not sliding, they kind of get stuck to each other, right? See how they kind of want to, it's like, it needs to get past that hump. And so the friction that happens between two surfaces that are not sliding and not moving relative to each other, that is static friction. Okay, that's a larger amount of friction. But once you can kind of get up over the hump, oh, okay, now it wants to go ahead and move more freely. And so that's static friction. Now, what kind of friction is between the wheels of a car and the road? Is it static or kinetic? It's static. Sure, the car is moving, but it's a different point of contact with the road, and that point of contact is not sliding. If it was sliding, well, that's bad, because then you would not be able to stop as fast. That's why ABS brakes, okay, anti-lock braking systems. That's why as soon as they sense sliding, they'll let the wheel rotate a little bit, so that way it gets maximum grip. You want to be at that point where you're slowing down as much as possible without actually sliding. And so here's what the transition point looks like between the friction force between sliding and not. So let's imagine that I have some sort of string that I'm going to attach to this object, and I'm going to pull it. So we're going to pull this object off to the right. Let's just imagine that I pull it directly to the right. And I pull it, it's not moving yet. I pull it harder and harder and harder and harder, and it just doesn't want to move yet. And so what's happening is you are going to pull it harder and harder and harder. So as we go this way, it's showing how much you're pulling. And then once it gets to here, so you're pulling harder, and the friction force is also going to pull harder until it gets to the point where you break it free of that static friction. And now it's going to drop down, and it's going to do this sort of wiggling thing as you measure the force of friction, because what's happening is now you're actually measuring the kinetic friction force, the force that is going to be acting in the direction opposite of your pull, and it's going to be a little bit wiggly because of those little bumps. Inclined planes, we have the force of gravity is going to act straight down, and of course we have the normal force that acts perpendicular to the plane. Be sure to draw that properly, and in fact I know that this is the right length because when I do a vector addition, okay, I'm going to bring this over. Notice what direction is the resultant force? The resultant force goes from the very beginning to the very end, doesn't it? It is parallel to the plane. That's the direction the box would slide, isn't it? Right? Right. So that is how long the normal force has to be in order for this to make sense, perpendicular to the plane. So as the inclined plane becomes increasingly large of an angle, the normal force is going to decrease. Gravitational force stays the same, but the normal force will decrease. And so next we're going to solve for the acceleration of the box down the plane. That'll be in the next video, which is actually, frankly, one of my favorite problems to solve. It just looks nice when it's done all nice and neat, and hopefully you guys will appreciate that. So I think with that, I'm going to finish on this whole, I talked about inertial reference frames. That's it. I'm done. I'm sorry it was a long one, but there's a lot to get through. I mean, for crying out loud, it's forces. It's Newton's laws. It's the basics of physics, man. Can't blame me too much. All right. So with that, I'm going to end it. And I hope you guys have a good one. I hope you learned something, and you guys contact me if you guys have any questions. So next, we'll be talking about the inclined planes and how to show the acceleration of a box as it slides down that inclined plane. Until then, you guys have a good one.